and then to upload it to your computer and just take little screenshots with that Windows snipping tool or whatever. If you're on a Mac, the Command 5 or whatever it is. Command Shift 5, that one. So that's, I think, the easiest way, and then just paste those in. That'll be probably the simplest way. You can use the digital ink, that works. The problem is if you need extra space or whatever, digital ink, if you start hitting return, it doesn't move with the page, so it's a pain in the neck. So it's a little easier to do it on paper pencil and do it the way we just talked about. So let's go ahead first and finish up this section. Today, after we finish this section, we're going to get to our applications. So we do most of the applications that you see in Calc 2 and Calc 3 tend to be physics applications, so that's what we'll be doing today. Force and things like that. We'll get to it in the next section. So at this stage of the game, we are finding the area of a surface, and the surfaces that we're creating are really symmetric. We're taking a curve and we're building the surface by rotating it. Again, when you get into Calc 3, you'll deal with more general surfaces. For us to go into 3 dimensions, it has to be in a way that has a lot of symmetry. So with this particular example, we're given this curve, y equals x squared divided by 4. On the x interval 2 to 4, we're going to rotate about the y-axis. So on Thursday, I mentioned that when we're finding the area of a surface, if it's generated by rotating around y, it's usually easiest to use dy. And if we take our curve and rotate it about the x-axis, it's usually easier to use dx. This says rotate around y. But the function that's given to us is presented as a vertical function, right? It's measuring height. It's presented as a y value. If we're going to rotate around the y-axis, we want to be measuring horizontally, right? The distance to the y-axis is a horizontal distance, so we're going to change the look of our curve by isolating the x instead of the y. That way we're measuring horizontal instead of vertical. So that's the first thing we're going to do. And I've done that right here. I multiplied both sides by 4, and then I took the square root, and I chose the positive square root because we're in quadrant 1, where the x coordinates are positive. When you take the square root of both sides, there's a plus or a minus, but in this particular case, we're choosing the positive square root because we're in quadrant 1. So there is our curve. Now it's measuring horizontal distances. And the second thing we have to do, if we are going to rotate around the y-axis and we're going to use a dy, we need to have y limits of integration. So we're going to convert the x limits. When x is 2, we plug it in here, and we get that y is 1. When x is 4, we plug it in here, and we get that y is 4. So we're just finding the y coordinates of those points of intersection. We're finding the 1 and the 4 coming from the 2 and the 4. So now we're good to go. We know that the generic formula here, recall that when we're finding surface area, the concept is that this representative point right here, we've got a point, we can say that it's at a random y value. When that point rotates around the axis, it creates a circumference of a circle, which is 2 pi r. And the idea is that if you take the circumference and integrate it with respect to s, so when you integrate with respect to s, you're imagining moving along the curve, that's going to give us surface area. So circumference integrated with respect to s. We don't know anything about s limits, so we have to convert the ds like we did when we were doing arc length. We convert the ds either to dx or dy with that formula. That's the arc length formula. So we know when we stare up here at this formula, we know there's a prime there on the x. We need a derivative. So let's start there. So let's find the derivative of y. This is 2y to the 1/2. we're going to use the power rule, so the 1/2 exponent comes down. 1/2 times 2 is 1. And then we subtract 1 from the exponent. 1/2 minus 1 is -1/2. So there's the derivative. And we are going to have to square it for this formula, so we can go ahead and just square it here if we want, just to keep it a little cleaner. That's 1 over the square root of x, 1 over the square root of y. And when we square that, we'll just get 1 over y. The square will undo the square root. The minus sign pushes it into the denominator. Okay, so that tells us that our surface area, they use capital S for that in this book. We're integrating with respect to y from 1 to 4. And then we have our 2 pi r. So that's the radius. R is this distance right there. That distance is the function. Right, we converted our function to an x value, so it's now measuring in the x direction 2 square root of y. 2 square root of y. So there's the 2 pi r part. The ds part is this. So that's the square root of 1 plus x prime squared. And we already squared x prime just above. So there's our setup. We have 2 square roots being multiplied together. To compute that, we combine them into 1 square root by multiplying the insides of each of them. So we're going to take the inside of this left square root, and we're going to distribute it to the inside of the right square root. And this constant stuff out here, we can bring that to the front. So we'll have this as our kind of simplified integral. When this yellow y goes inside, y times 1 is going to be y. Y times 1 over y is just 1. So there will be our simplified integral, which we can use the power rule for. So this is y plus 1 raised to the half power. Go through the whole add 1 and divide thing. So we're going to have y plus 1 to the 3/2, adding 1 to the exponent. Dividing by 3/2 is the same as multiplying by 2/3. And we don't have to do a reverse chain rule because it's y. It's not 5y or 6y. It doesn't have a coefficient. Well, the coefficient's 1. And so we don't have to do any extra RCR, no reverse chain rule. If there was a 3 in front of that, we would then have to divide by 3 for reverse chain rule. But we don't here, so we're good. There are the limits of integration. So we are going to have 8 pi divided by 3 out in front. And now we're going to plug the 4 and the 1 in there. We're going to get 5 to the 3/2 power minus 2 to the 3/2 power. And that's a totally fine answer. But if you're wanting to simplify this for some reason, good measure, or because you were asked to do it by somebody, you would do that. This is a totally fine answer, though, right there. But if you want to simplify it, that is the standard way to simplify 3/2 powers. Any part of that you want to ask about? Good.
Why did it switch to 2 to the 3/2 power?
Say that once again.
Why is it 2 to the 3/2 power?
When we plug in a 1 here for this limit of integration.
That's right, my bad.
You see it?
Yeah, my bad.
Any other questions on it? All right. Here's another one. Going around the y-axis. This one is presented as a horizontal function already. It's measuring horizontal distance because the x is isolated. So it's already in the right format. We don't have to do any manipulation there. And we're given y limits of integration right away. So here we have less work to do in terms of setup. So the surface area, 2 pi r. So 2 pi, we can pull that to the front right away if we want. And we're told the limits of integration are 2 to 10. R, or the function, these are the same, right, those are the same right there. R is the distance over to the curve, so that is the function. The function is measuring the distance away from the y-axis, which is the radius. So that function goes in next. So we have square root 12y minus y squared. That's the r, 2 pi r, so that's circumference. And we integrate with respect to s, but we don't know anything about s, so we convert to the y's. So then we're going to have square root of 1 plus the derivative squared. So once again, we have to take a derivative. So with all these arc length and surface area problems, we're always taking a derivative of the function. So let's do that up here. And maybe I'll write it with the 1/2 exponent just because we know that it's easier to differentiate when you have it written that way. So x prime, we bring the half down. The base stays the same. We subtract 1. And then we multiply by the derivative of the base. So that's the chain rule. Let's rewrite this to make it easier to square it. There's two things I see. This 1/2, that can be distributed into that numerator right there. That 12 minus 2y is in the numerator, so that could be distributed into that. And then I also see that this negative exponent could turn into a square root in the denominator. So if I simplify this, this is going to be 6 minus y divided by the square root of 12y minus y squared. Let's make that a little bigger. I'm going to move this down just to give us a little more space up there. So 12y minus y squared goes in here. And if we square it, let's go ahead and square it before we put it in down here. So 6 minus y quantity squared is the numerator. And when we square the denominator, the square root vanishes. So we have that. So there's x prime squared. That's what's going to drop inside here in the second part of the square root. So that whole quantity comes in here, 6 minus y quantity squared divided by 12y minus y squared with respect to y. And once again, we have two square roots that are being multiplied together, so we're going to distribute the contents of the first square root. We're going to distribute those contents to each of the terms over here. And we're so lucky because that second term has a denominator that's equal to what we're distributing. So that will just cancel. So 2 to 10, big old square root, 12y minus y squared times 1. And then we're noticing when this yellow part distributes to this fraction, it matches the denominator, so it just cancels the denominator. And we're going to square out that numerator. So let's square out that numerator right there. So that's going to be plus 36 minus 12y plus y squared. And whoa, boy, do we get some cancellation. 12y, positive 12y, negative, those are going to cancel. Negative y squared, positive y squared, those are going to cancel. Square root of 36 is 6. So the 6 is going to come out to the front and give us 12 pi. So this is what we are left with. Square root of 36 is 6. 6 comes to the front, multiplying by the 2 to give 12. All we're left with is the integral of dy. And what is the integral of dy from 2 to 10?
Is it like 10y minus 2y?
Almost. There's no y, though. It's just 10 minus 2. If you were actually doing the integration, that's where your y might come from. So if you were going to do the math here and not just cut to the chase, you would have the integral of dy as y from 2 to 10. But as we start to see this more and more, you realize that, oh, every time we integrate a differential, the result is just the length of the interval. So we would end up with 12 times pi times 8. That whole thing is just going to reduce to 10 minus 2. And so we'll get 96 times pi. So as you do more and more of these, it's completely fine just to cut to the chase right there. You can just go straight there. Integrating a differential gives you the length of the interval. That'll be our surface area. Okay, one more example here. We have a minor application. Some of the applications are very contrived. We're really just finding surface area. The applications in the next section are more legit. So this says that we have a portion of a sphere. We're going from -8 to 8. Here is a graph of that portion of a sphere. This is a circle centered at the origin of radius 10. And we want to go from -8 to 8. So that portion of the sphere is going to be rotated around the x-axis, creating kind of a shape similar to the other one that we just did, but it's this direction. And then we're going to paint it. And we're told that the paint is that thick, 0.0015 meters thick. All right, so same idea. If we're going to find surface area for a surface of revolution, we go 2 pi r, circumference, multiplied by ds. 2 pi r is right there. ds, we convert to dy or dx. In this case, we're going to convert to dy because we're going around the, hold on here, let me just think about this for a second. I have the formula. Should this be an x prime? If we're going to go around the x-axis,
Should be y prime.
should be y prime, and what should the differential be?
dx.
Dx. If we're going to go around the x-axis, how thick is this How thick is, this element? It's dx thick, right? If you draw a vertical element, you're always using a dx. If you draw a horizontal element, you're using a dy. So this should be, I will correct this as soon as I get out of here. That should be a y prime and a dx. Yeah. It's my first pass through these notes, so there's some typos that I'll have to catch as we go through. Does that make sense to everybody? If we're going to rotate about the x-axis, we want to use a dx. And if we've written our function, where is our function? Oh, right here. If we've written our function to measure vertically, then we're going to use a dx. So looking at this picture, we know we should have a dx, and we're going to go around the x-axis. So that should be a dx, and that should be a y prime, because we are using a function that's measuring vertically. All right, once again, we need a derivative. So we've got our function here, simplified in a way that we can take a derivative pretty easily. We're going to use the power rule, 1/2. That's going to come down. We subtract 1 from the exponent. We multiply by the derivative of the inside. We get -2x for that derivative. We can simplify a little bit. We see this 2 here and that 2 there. One's in the numerator, one's in the denominator, so we get some cancellation. So I'm seeing -x divided by the square root of 100 minus x squared. So there is our simplified y prime. We know in our formula we're going to have a y prime squared, so we can kind of square it here just to get it nice and simplified before we put it inside. When we square the numerator, we'll end up with just x squared. When we square the denominator, the square root will vanish, giving us that. All right, so then our surface area will be 2 pi r. We can pull the 2 pi to the front. And we're integrating from -8 to 8. So we could use limits of integration -8 to 8. Or we could use symmetry and go 0 to 8 and double it. All right? Symmetry would work here. So let's do that. So I'm going to move that integral over. I'm going to put another 2 here. And then we're going to go just 0 to 8. And so this 2 is by symmetry. Whenever we can have a limit of integration that's 0, that tends to help us. So now we've got our 2 pi r. There's r. That's measured by the function. So that drops in right here. So now we're at the 2 pi r. Now we're doing the ds, which is this part over here. That's the square root of 1 plus y prime squared. And then we have a dx. That's an x squared. And we're in a familiar place where we have 2 square roots being multiplied together, so we want to combine those. And we have seen that the way you combine 2 square roots, or you know this from algebra, that you multiply the insides together. So this inside is going to distribute to the inside of the second one. So it's going to be multiplied by both terms. When we multiply it by the first term, we have 100 minus x squared. When we multiply it by the second term, we end up with just x squared, because the numerator and the denominator are canceling each other out. All right, those x squareds cancel. Square root of 100 is 10. So we end up with 40 times pi. And our integral 0 to 8 dx. Integral 0 to 8 dx is going to be equal to 8. So 320 pi will be our answer. Because this right there has value 8. So that is our surface area. Now this had a contrived application here. It said, okay, we revolve around, we find the surface area, and they wanted to know what the volume of paint is, rounding to 2 decimal places. So we're going to take our surface area, multiply it by 0.0015, and then approximate it. So to finish this thing off, all we need to do is go to our calculator. 320, that's not 320, 320 times pi times 0.0015, and that's our answer. So then they said to round that to 2 decimal places. So we'll just grab that thing, drop it in. And then we round it to 2 decimal places, getting whatever we get. And in this case, 1.51 would be our answer. So the volume of paint will be 1.51. Were we dealing with meters? Yeah, we converted the 0.0015 to meters, so cubic meters. So in this case, they do give us units. Most math problems we don't. We just skip out on the units. But here we have them, so we include them. How does that feel so far? Reasonable. Got to do some practice. So remember, worksheets are due Thursday night by midnight. And then we have an exam that's not too far off. So we are sitting on this Tuesday right here. We are going to have an exam a week from Thursday right there. So a week from Thursday, we have our first exam. We'll do review on the Tuesday before, right there. So the section that we are about to enter it's really in this class, it's really the only section that's totally devoted to applications. And they are, again, all physics applications. So we will, so you'll see these applications probably in another context in physics at some point. The first one has to do with mass. And generally, when we think of mass, we are finding mass by multiplying density times volume. So density is a concentration of mass. You think of it as grams per cubic centimeter. So that's sort of typical. But we can also have two-dimensional and two-dimensional and one-dimensional mass. If we imagine a thin plate, you can measure density in 2 dimensions and have it be grams per centimeter squared. Or if you have a wire, you can imagine density as one-dimensional density, and we would measure it in grams per centimeter instead of grams per square or cubic centimeter. So we have 3 different scenarios. The one that's the most intuitive is you've got a solid object. You can imagine the density is the concentration of mass, and we're going to use the grams per cubic centimeter. That's the one that's the most intuitive. But we do have those other 2 applications, other 2 types of applications that you will see. Now, this basic formula, in this class, we constantly are going to talk about the basic formula for something. Like, okay, we need the area of a shell or a cylinder, 2 pi r times h. We need the area of a disk, 2 pi r squared, whatever it is. The basic formula for mass is density times volume. The thing that changes is when the density is not uniform. If the density is variable, then you can't just do that straight multiplication to get to your mass. If this density is variable, then we have to jump to an integral. That's what an integral is going to do. And this is the whole Riemann sum idea. If we take our object and start breaking it apart into little tiny pieces, on a little tiny piece, you can imagine it roughly having uniform density. Right? On a little tiny piece, if you zoom in small enough, you have uniform density. And so you're finding the mass of all the little pieces, and then you add them up, and then you take the limit, and you get the total mass. You get the exact mass. So we're going to start out with an example, 1 dimension. So 1-dimensional object. If we want to get to mass, we have to integrate density. And if you look inside, one of the tricks they teach you in physics and in math is that the units of what's inside should match the units on the left. And this integration symbol is just summing up. When you look in here, you should see a tiny mass. Right? The density at x, and then a little differential in x. That's going to give you a small region, small volume, small length, depending on what the context is. In this case, we're imagining it as a small length of wire, a tiny piece of wire. So we have the density at a point, and then multiplied by a tiny change in x. So that's going to be the mass at that for that little piece of wire. And then the summation sign or the integral sign adds them all up. So with 1 dimension, we're dealing, in this case here, grams per centimeter. So density is grams per centimeter. dx is centimeters. Grams per centimeters times centimeters gives us grams. And then we sum up all those grams to get the total grams, which is the mass. So that's our idea. That's the concept there. So let's try one of these. These ones will not be on the exam. These two are it's so simple, but it illustrates the concept. So we've got this mass function right here. We're imagining a very thin bar. So we're imagining one dimension. So like a wire, imagine a wire. So we've got this one-dimensional density, which is going to correspond to a one-dimensional mass. All we have to do is integrate it on the interval. So the mass here, all we do is integrate from 0 to 1, this function, and that's it. Can you guys close those doors? It's a lockout thing, so we can keep doing our thing, but we just have to have the doors closed. This is fake. Don't be alarmed. It's all fake. There's no. Now that would be quite the thing if you wanted to be a derelict. You know, find out when they're going to do one of these things, and then like strike now. Come and steal all the money from upstairs.
Money upstairs?
Oh wait, we're a community college. There's no money up there. Wrong place to rob. Don't rob a community college. Go rob the snack bar up there. You might get $30. Okay, so that's the idea. So the concept here is that we've got variable density. We want to find the mass of a wire. All we do is integrate the density to get mass. So this kind of falls in line with a lot of the concepts we've used already. If you integrate distance, you get area. If you integrate area, you get volume. Here, if you integrate density, you get mass. So this is our concept. This one, same thing. We have a density function that has a variable in it. So we can't just multiply this density times the length of the interval because this density is changing. So that's why we have to use integration, which is our major Calc 1 idea. Integration. Here we have a linear exponent on an exponential function. The integral of an exponential function begins with itself. And then we do the reverse chain rule by dividing by the derivative of the exponent. So we get that. So we have negative 5 over 2 in front. We're going to plug in our upper limit. We're going to plug in our lower limit. And we are going to end up with e to the negative 8 minus e to the 0, which is 1. And that is going to be our mass. Right there. Now mass has to be positive. You can't have a negative mass. Is that a positive number?
Yes.
Very definitive. I like that. Yeah, that is a positive number. Everyone see it? Positive number? E to the negative 8 is minuscule, super small. E to the negative 8, 1 over e to the 8, very small. Subtract 1, that's negative. So negative times negative will give us positive. So that will work out fine. Okay, so that's all we're learning right there is the integral of density is going to give us mass. That's going to lead to some of these more complicated problems. So the next concept, now that we have a little bit of under our belt, mass integral of density. Same idea here. We're going to have a basic formula if you have displacement. So if you apply a force to an object, you're pushing your snow shovel. Oh, wait, there's no snow in this state. If you're doing whatever you're doing, you're pushing the wagon because it's so nice out. As you're pushing the wagon, you're applying a force over a distance. That means work is done. When force displaces an object, work is done. So if a force is moving something, work is done. And work will be force times distance in the most basic sense if the force applied is constant. So if you're applying a constant force to something, you're lifting something, constant force, then you can get away with this simple formula. Typically, the force is not constant. The force is variable. And if the force is variable, then we need an integral. Okay, and so that's where calculus comes in. So the idea, if we have a variable force, so you can see this function is not constant. So that's a picture of the force function. It's not constant, so that means we're going to need an integral. So the idea, once again, is that we look at little pieces. If we have our total interval, if we zoom in on a tiny, tiny interval, on that tiny interval, the force is essentially constant. So you can get away with a force times distance on a tiny interval. That's what this is representing. That's a Riemann sum. We take the limit of the Riemann sum. It turns into the definite integral. And lo and behold, we get another integral when we have a variable quantity. So in this context, we integrate force to get work. If you look inside the integral, if you treat that as one thing, that should have the same units as the left-hand side. We check. The units of force are newtons. The units of dx are meters. So we have the units on the inside being Newton meters. That's what we use to measure force, Newton meters, aka a joule. So another word for a Newton meter is a joule. You can use either in this class. Doesn't matter. They are the same. A joule or a Newton meter. So newtons times meter gives Newton meter. That matches work. Work or Newton meters for joules. All right, so let's try one. So spring, this is the most common application. When you go into a physics class, you'll do springs because springs have a very cool force function. It's linear. Simplest type of force function other than constant. Simplest variable type of force is a constant. So it might not be intuitive. I mean, we all have the experience that as you compress the spring, it gets harder and harder to keep compressing it. But it doesn't feel linear, though. It almost feels more like it's exponential. It's like getting really hard really fast. It doesn't quite match with what we think of as linear. But it is. It is linear. So the forcing function for a spring is linear, whether you are compressing it or stretching it. When we conceptualize the spring, we think of it just sitting there in equilibrium, and then we either compress it or we stretch it from equilibrium. So we're going to put the origin at the end of the spring, and if we are pulling it, we're going to say the force is positive, and if we compress it, the force is negative. So force is a vector. One direction is positive, another direction is negative. Okay. Okay, we've got this force of 15 newtons we need, maybe you remember in algebra when you did those half-life problems, the question was, what is the half-life of some radioactive isotope? And they give you you find the half-life by looking at you get that constant, what do they call it? Like every isotope has its own decay constant, and you use the half-life to find that decay constant. And it's that same idea. Like every isotope has its own decay constant. It decays at a constant at some rate. Every spring has its own spring constant. So we use some data point in order to figure out what the constant is for the spring, just like we figured out the constant for an isotope, using the half-life. So typically you knew the half-life so you could find the constant. So here they give us a data point. They say, suppose the force of 15 newtons is required to stretch or compress the spring 0.25 meters from equilibrium. So that's going to give us enough information to find the K. So the force for any spring is given by this Hooke's law, Kx. We don't know the K, But we can find the K because they tell us that it takes 15 newtons to stretch the spring 0.5 from equilibrium. So we're going to have K multiplied by 0.25 from equilibrium. And that gives us the K. Divide by 0.25 or multiply by 4. So this is going to tell us that K is 60. So that is the spring constant for this spring. So this tells us that for this spring, the force function is 60x. That is the force function for this particular spring. The force will always be 60 times x. Okay. That's part A. So part A, we need to find that spring constant. Spring constant is 60. Part B, how much work is required to compress the spring 0.2 meters from its equilibrium position? So we're starting with the integral. The work is the integral of force. So we're starting at equilibrium, and we're going to compress it 0.2 meters. So what should the upper limit of integration be? Negative 0.2. So when we imagine our spring in equilibrium position, it's sitting there, 0 is the right end, and if we're going to compress it, we're moving in the negative direction. So we're going to go to negative 0.2 meters. We're going to integrate our function. So that'll be the work done to compress it. Yeah?
Would -2 be the lower limit?
No, because we're starting at 0. The lower limit is where we start. So that's the end of the spring in the equilibrium position. And then we want to then apply the force and compress it so that we end up with the front of the spring at negative 0.2. So now your question, though, if you don't like this, right, normally when we do an integration, we're going from left to right. We could flip this, and if we flip it, what would we have to do to the integral?
Like make it negative.
Multiply by -1. Yeah, so you can always interchange the limits if we, prefer to have it go from 1 to 3 instead of 3 to 1 kind of thing. We don't have to, though. Notice what happens here when we do the integral. This is going to be 60 x squared divided by 2. We can make that 30 right away. So that's going to be 30x squared, 0 to negative 0.2. We're going to square that number, right? And so it's going to turn positive. And we're going to have 30 multiplied by, I'm going to write that as a fraction. It's going to be a little easier to write it as fractions. So that's 1/5. 2/10 is 1/5. So we have that. When we square it, the minus goes away. So we're going to end up with 30 divided by 25. Cancel out the 5, and we're going to get 6/5 work. Joules or Newton meters, does not matter what you use. So we're going to go, ooh. So we get that. How much work would it take to stretch it 0.2 meters? Same amount, right? And you can see that from the square. If we went from 0 to positive 0.2, doesn't matter. When you plug it into this square, it's going to become positive. So the work done in compressing or stretching is symmetric. It matches. Yeah?
Can work be negative?
Work can't be negative. Yeah, if an object is displaced, work is done, which would be positive.
So with these spring questions, will you always have a square in it?
Yes,
Okay.
because you're integrating a linear function, so you'll
Yeah.
always get a quadratic. Yeah,
Yeah.
that's right. Yeah, with the spring. With the spring is the easiest one, so yeah, that's what makes it the easiest one. You're always integrating a linear to get a quadratic. So let's try this one. They make this a little more complicated. So how much additional work is required to stretch the spring 0.3, so an additional 0.3 if it's already been stretched to 0.25. So here, the beginning state is 0.25 from equilibrium, and we want to stretch it an additional 0.3. So what's the upper limit of integration going to be? 0.55. That's where the end of the, so we've taken the spring and we've stretched it so the end of the spring is sitting at 0.25, and then we're going to stretch it an additional 0.3, so the end of the spring is going to be out there at 0.55. And it's the same force function. So we have that. So once again, we're going to get 30 times x squared. It's going to be a little easier here if we convert these to fractions. So let's make that 1/4. We're going to make that. That's going to be 55 100ths. So we can divide out of 5. 5 goes into that 11 times. 5 goes into 120 times. So we'll have that. The problem with decimals is that when you get to your final answer, if you have decimals there, you don't know if there was a rounding or no rounding. And so it's nicer to use exact numbers whenever possible. So 30 times 11/20 squared, we'll get 121 over 400. Minus 1/4 squared is minus 1/16. Maybe it's actually easier to not simplify this one quite the same and to, well, no, never mind. You know, we could write this as 5/20. Maybe let's do that. Let's do that. That'll be a little easier. Everyone agree that that's 1/4 with the same denominator? Still a quarter. It'll just be easier to combine these fractions. Or you can just get a common denominator once you've already done it. Doesn't matter. So that's 30 times, whatever that is, 96 over 400. And then we have a sequence. If you have your calculator, you of course can do this probably much faster. I'm going to just ditch a 0 first, so we have that. All right, so what's that going to be? 4 goes into 96, correct? So 4 goes into 40 10 times. 4 goes into there twice. Times 4, 24. And we can, yeah, this gets tedious if you don't have your calculator. So we get 36 over 5. That would be our work, and that's in joules. So that's the additional work. They didn't ask us how much work was done in stretching it that first 0.25, that first quarter unit, whatever it was, meters, centimeters, I forget. Okay, so once again, our basic concept is if we integrate force, we are going to get work. So yeah, meters. Any questions on that idea? So integrate force to get work. Integrate force to get work. Force times distance is work. Force times distance. So, force times distance is work. Don't forget that. Let's do 2 more spring things. So, you all do A. You all work on A. And then we'll do B together. So, work on A. Find the force. For that particular spring. And I will take roll. Anna Karina is here. Allie is here. Cole. Is Cole here? Remember, Richard is not here. Hayden is here. Henry is here. Daniel is here. Kaylee, River, Errol. Sam is not here. Ari is not here. Yam is here. Paul is here. Walter. No Walter. Sean. Shelby, Connor, Jojo, Corbin is here. Mia is here. Zach's here. Landon. Ah, yes, 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 yes. Link is here. Okay. Spring constant 500, no mystery. And we want to stretch at 0.1 from equilibrium, so work. Limits of integration. What should the lower limit be?
0.
Yeah, 0, because it's from equilibrium, so we're starting in the equilibrium position. We're going to end up at 0.1, which I'm going to write as 1/10.
Oh, I did 0.4. from
Yeah,
the
so we were
very
trying
top
to
right.
get-
I missed something here. Following springs, 0.4. What's the point? What's the 1/10 then?
That was saying that's how.
Oh, that was for the initial condition. Yeah, thank you. Yeah, thank you. Yeah, 0.4 from equilibrium. So 0.4, which I will write as a fraction nonetheless. So that's 2/5. And then we integrate that force function, which is going to be 500x with respect to x. So we'll get 250x
Where
squared.
does the 500 come from? I see 50 there, 50 newtons.
And then we multiply by 10 to get k. So force is kx, so they tell us the force is 50 newtons to stretch or compress 1/10 of a meter. So we multiply both sides by 10 to get the 500. And then we'll end up with 250 multiplied by 4 over 25. So 40? And we're doing work, so joules or newton meters, either one. I like the rotation. Close enough to level. Now the second one is a little weirder, the second part here. The second part does not give us what we typically are thinking of as initial conditions. Right? Normally they're giving us a force and a displacement so we can use the F equals kx. The second one, notice it says a spring that requires 2 joules of work to be stretched 0.1 from its equilibrium. So let's just write down what they're saying. We know that work is the integral of force. They're giving us work. So work is 2 joules, and we're going to stretch 0.1 from equilibrium. And we don't know what the forcing function is, so we can just write it generically as kx. Force is kx. We don't know what k is, but notice this equation only has one unknown. The only unknown here is k, so we could solve this for k. And there's only one unknown. On the right-hand side, we know that k is a constant, so we can integrate this still. That k factors out to the front, and we're going to go from 0 to 1/10. So we have 2 equals, let's finish off the right-hand side, and then we'll go from there. So the k over 2 is constant. 1/10 squared is 100th, minus 0. We have that. And now we solve for k. So on the right-hand side, we have 200 in the denominator. We multiply both sides by 200, and we'll get that k is 400. So that is going to be our spring constant for the second one. So the force function would be 400x. That is our force function. And then they ask the same question. So this one had a spring constant of 500. We want to go from 0 to 2/5. So we're going to do the same thing here. We want to go from 0 to 2/5. So the work done in stretching it from 0 to 2/5 we're going to end up with 200x squared from 0 to 2/5. So we'll have 200 multiplied by 4/25. We'll get 32 joules. That's how much work it will take to stretch it to 0.4 or 2/5 of a meter. And does it make sense that it's fewer joules than the other one? The spring constant of the other one was bigger, so it takes more work to compress it or stretch it. This one has a slightly smaller K value, so it's going to take less joules to compress or stretch. Okay, springs. Now, let's get to the stuff that's a little more calculus heavy. Springs are horizontal. Most of the force stuff we're conceptualizing so far is horizontal, pulling a wagon or something. We haven't taken gravity into consideration yet. So now we're going to go and think about force that's due to gravity. All right. So Newton's law says that when we're using gravity, when we're moving vertically, that force is going to be mass times gravity. So that's now the forcing function. The forcing function is mass times gravity. Work is still force times distance, as it always is. It's just now that the force is given by mg, Newton's law. Force is mg. So we're going to have two types of problems. We're going to have pumping and lifting. They're going to be the same in terms of the setup. So if we look at this, gravity is a constant here. And the idea is that if we have some vessel that's filled with some liquid, we either want to pump it out the top or drain it out the bottom. So let's first just talk conceptually about that. If we've got some vessel filled with liquid, if we're pumping it out the top, the pump is doing the work. If we drain it out the bottom, if we just pull the plug in the bottom, gravity is doing the work. Okay? So, now, let's think about a concept for a second. Let's suppose our vessel is not symmetric like a cylinder. Let's suppose it's like this parabolic looking thing. Do you think the works would be the same? If you pump out the top or drain out the bottom, do you think the works would be the same? The magnitude of the work?
No.
And the answer is no. And so we'll see why that is in a second. You might already have an idea. If you think in your mind about the volume near the top, if you take a cross-section, if you have this vessel, this cross-sectional, if you take a slice, so remember a cross-section is paper thin, but a slice, you puff up that cross-section and turn it into a slice by multiplying by the little height, the dy. This slice of water, if it's water, this slice of liquid is bigger than this slice down there, more volume in it. But if you pump out the top, this bigger one has less distance to travel, whereas this bigger one here would have more distance to travel if it goes out the bottom. So the work that would be bigger would be the work done by gravity, because this bigger slice would have to travel further. Here, going out the top, the smaller slices would have to travel further instead of the bigger slices. So that's kind of an idea of why the work coming out the bottom would be bigger in magnitude than the work coming out the top. If it was a cylinder, the works would be equal, if you had that symmetry, if all the slices were the same. Okay, so the work required to drain this water out the top, the AB is just our bottom to top. These pieces are density, gravity, cross-sectional area, distance traveled, and then our differential. So there's a whole bunch of stuff in there. Looking at that, and the way they build the Riemann sum, the idea, once again, we're going to look at slices, we're going to look at cross-sections and break it apart into small little slices, and on any one slice, the work done is going to be, it's going to be constant to lift out one slice, and then we add up all those constants to get an approximation. We take a limit, and when we take the limit, we get the exact work done. So each one of these slices, the force is going to be variable for multiple reasons. A, they have to travel a different distance. B, they have different diameters or radii if you think of them as circles. So there's a lot of variation going on. That's going to be our formula. We conceptualize the formula by this type of thing here. We know that work is force times distance. So we just want to sort of confirm that all of this inside is going to be work. Here's how we're going to think about it. Mass is density times volume. So there's density. Volume is given by area multiplied by distance. Now, one thing that is 6 of one, half dozen of another is right here. Both the dy and the distance traveled by a cross-section are both measured in units of length. Right? dy is a little change vertically, units of meters or centimeters. The distance that a cross-section might have to travel, centimeters or meters. So when I think of this mass as density times volume, certainly density is right there, but I could highlight this A and this dy just as easily as I could highlight these two. Doesn't matter. They both have units of length. Technically, the A and the dy is what builds the slice. A is the cross-sectional area and dy is its thickness. So it's better, conceptually, you're thinking of the A grouped with that dy. But if we're purely looking at units, it doesn't matter. This has units of centimeters, that has units of centimeters, doesn't matter. What's important is that when you group these two together, you get volume, right? Area, meters squared, centimeters squared. Distance, same thing. Together, that is volume. So volume times density is mass. So now we have mass. Gravity, mass times gravity is force. So that tells us that all of that is force. All of that is force. And we know that work is force times distance. So now the inside, if we include everything, including the differential, we have units of work. So that really is just the integral of force. So that is going to give us work. Now, when you look at that hideous looking formula, we need something, we need a better way. You can't just memorize that unless you're really good at memorizing things. There's no way you're just going to memorize that without some sort of acronym. You need something. If I look at that, there's no way I would just remember that. I don't think you would either. So we will bring up the next slide, and we'll take our break, and we'll leave this up here. Here is going to be our acronym. ADD volume. This is going to be force times distance, so this is going to be work right here. ADD volume. And then I've got the units all laid out here, just like I did talked about on the previous slide. So A is going to be acceleration, D is going to be density, Second D is going to be distance. Volume is going to be the volume of a slice, which is cross-sectional area times dy. All right, let's take our 10-minute break, and then we'll dive into that crazy formula in a little more detail. And figure out how to pause.
I was up to like 4 something last night.
Oh,
And didn't
ouch.
get much of it done because I was so tired.
Yeah, that gets exhausting. Okay. So, I claim that this acronym is going to be enough for us to understand this really well. And as we do some examples, it's all going to start sifting into place. I want to point out that I put the volume piece in parentheses because it's a tiny volume. It's not the volume of the whole vessel. It's the volume of a slice. And remember, for us, the volume of a slice is the cross-sectional area times dy. So those parentheses are supposed to be a reminder that that's a tiny volume. It's not the volume of the whole tank. All right? Now, the book does the one-dimensional case before it does the three-dimensional case. I'm going to jump to the three-dimensional case first because that's what the formula is based on, a three-dimensional case. And it's a little easier to conceptualize the three-dimensional case than the one-dimensional case, actually. So I'm going to jump to the three-dimensional case, then we'll come back and we'll do the chain and the rope. So we're going to jump to the cylinder. This is the easiest one. So here, if we have a pump and we're going to pump the water out the top, or gravity, water out the bottom, the work done is going to be the same because of this symmetry here. All the cross-sectional slices have the same volume. Cross-sectional area is the same no matter where you draw it. So the first thing is that we're going to write down work is the integral of ADD volume. And that's going to be enough for us to piece it all together. So ADD, acceleration, density, distance. It could be acceleration, density, depth also once we get into the next section down if we're dealing with another application. So that second D can be thought of as distance or depth. Does not matter. So when you're thinking of that D, we imagine our cross-section, and it needs to be pumped a certain distance to get out of the tank, either down or up, depending on which way it's going. So that's it. It's measuring distance. And that's what makes the force variable here. Depending on how far that slice has to be pumped, the further it has to be pumped, the more force it takes, which corresponds to more work. So that's why we need an integral here. So we just go straight across the board. So we're going to deal with water. The density is a constant. Density of your liquid is going to be a constant. So acceleration due to gravity, that's a constant. So these first two are going to be constants in all of these types of applications. So acceleration due to gravity, constant. Density of water, constant. Now we have the distance traveled by a representative cross-section. So let's come to our vessel over here. I'm going to draw a representative cross-section. That's two-dimensional. It's got some radius there. That's our representative cross-section. It's at a height of y. And whenever we choose a horizontal random, it's at y. Vertical random is at x. We're using gravity here, so everything's going to be with respect to y. This tank, we are told, is 8 meters in height, and the radius is 2 meters. So the radius across here is 2 meters, and this height, this total distance here, is 8 meters. So the distance traveled by this representative cross-section is what? The distance traveled is going to go from there down to here. That is the second d. What is that distance?
Y.
Y is going to measure this distance, right? Y is measuring the distance from the base up to here.
H minus Y.
8 minus y. Yeah, h is 8. So 8 minus y. Everyone follow that? If the total distance is 8 and this distance is y, the complementary distance is 8 minus y. So that is going to be the distance traveled by our representative cross-section. That's how far that cross-section has to travel to get out. If we're pumping out the top. We're pumping out the top here. All right. So that's ADD. Two of them are constant all the time. Now volume. By volume, we mean volume of a slice, which is the cross-sectional area, but then we throw in some thickness. So that thickness is dy. So this is going to be cross-sectional area. It's a circle of radius 2, so it's pi times 2 squared times dy. That is the cross-sectional volume right there. Those are equal. We take our area and multiply it by dy. That's the volume of a representative slice. All right, and then our limits of integration, this tank is filled, so 0 to 8. Lots of constants right here. Right, so we're going to pull that constant out to the front. That's going to be a 9800. Oh, that is constant also, 4 pi. That's going to come out to the front. So all that's left inside the integral is 8 minus y. So if we can piece together the formula here, that's a pretty easy acronym, ADD volume. A and D are both constants. That's a pretty simple variable to come up with. The distance traveled, it's vertical, so it's always upper minus lower, which we've done a lot of already. And then the part that's probably the heaviest lift is this volume of a slice. So we draw a representative slice. It's the cross-sectional area times dy. And so one of the common mistakes is that when you see volume, you want to write the volume of the whole tank. Just the volume of a slice. Now we can finish this off. I'm going to just leave this in front for a second. Maybe we'll get lucky and have some cancellation. So this is going to be 8y minus y squared over 2 from 0 to 8. So we're going to have 9800 multiplied by 4 pi multiplied by 64 minus 64 halves, which is 32. So we have to just multiply all that together. 9800 times 4 times 32. $9,800 let's see, times, is it the asterisk? I can't even see this keyboard. I guess that's an asterisk. No, that was an exponent. Dang it. Which one is the asterisk? That one? 4 times 32. Was that all the numbers? So that amount of pi. All right. We got them all. So that number, pi. And now these problems do have units in them. We're finding the work done, so joules. So now we're using units all of a sudden. Don't need that. Okay, so cylinder. That's the work done and emptying a cylinder. EDD volume. Let's try another one. So most of our problems are going to have variable cross sections, which is going to make it much harder. For that cylinder, every cross section was pi r squared, where r was 2. So let's up the ante. So we've got a semicircular trough, has radius 1 and length 4. So let's draw the face of the trough. So the face of the trough looks like that. The radius is 1. Is that what I said? Radius 1. And the length is 4. So radius is 1. So this dimension is 1. Now we need to come up with an equation for this. Because remember, when we look at a cross section here, it's going to be a rectangle. So a representative cross section, we're going to draw across here, across the face, and then all the way down to the back. Right? So a representative cross section is going to look like that. It's going to be a rectangle. That's going to be area, and then we multiply it by dy, and we'll have a slice. So let me draw that representative cross section over here. We're going to be going across a semicircle. So we need the if we want to find the width across here, if we want to find that width, we're going to need to know the equations for the right and left edges. All right, so we're going to position, and this is your choice. I will always position circles and things like that on the x-axis, like I've drawn it. And then, of course, the vertical axis is coming right down the middle. So we've got this scenario. That is the center going to that point right there. Okay, so that's what we have. So now we need the equation for this circle that has center 0, 1. So we want a circle with center 0, 1 of radius 1. So basic circle is x squared plus y squared equals r squared, but this one is shifted a little bit. It's shifted vertically, so we have to shift the y coordinate. So that's going to be the equation of our circle. Center 0, so it shifted 0 in the x, shifted 1 in the y, radius is 1. Now, if we want the right edge, the right side of this circle or the left side of this circle, what letter do we want to solve for?
X.
X. X measures horizontally. So if we isolate x, we'll get a plus or minus, square root of the other stuff. Positive square root will be the right edge. Negative square root will be the left edge. So let's isolate x. And I'm going to square out this thing here with the y's. And when we square that out, we simplify it and get that. So we get x equals plus or minus the square root of this. The right edge here is going to be x equals the positive square root. The left edge is going to be x equals negative square root. All right. So now we have enough information to start filling in our blanks. So we come, we write our generic formula down. Writing the generic formula down is always a good idea. So the integral. We have this, we want to empty the entire trough. It's filled with water. We want to pump it right out the top. All right? So what should our limits of integration be? So if we're imagining this filled with water, we need to pump out every cross section from 0 up to 1. All those cross sections have to get pumped out. 0 to 1. If we were pumping the water right out the top, it's 0 to 1. If we're pumping it out this pipe that we're going to talk about in part C, it's still 0 to 1. All the water from 0 to 1 is still getting pumped out. It's just that the distance traveled might be further if there's a pipe that has to go up and out. But you still have limits of integration 0 to 1 because that's where the activity is. 0 to 1, you're going to do something. All right, so now we have our ADD volume. A, acceleration due to gravity, 9.8. It's a constant. D, density, acceleration, density, distance. Density. We're dealing with water. Density is constant with a density of 1,000. Now, distance traveled. Okay. So our representative element here is at a random y. The distance it has to travel is right out the top. So what is that distance?
1 minus y.
1 minus y. 1 is at the top. Y is a partial distance up that, the complementary distance. Top minus bottom. 1 minus y. Now volume. Volume means the volume of a slice, not the volume of the trough. So we're now imagining our cross-section having a little bit of thickness. So we're going to run, this thing all the way around. It's going to look like a total mess. So we take our cross-sectional area and multiply by dy. That gives us the volume of our representative slice. So we need area multiplied by dy. So the area of the rectangle, the area of our representative rectangle, is going to be W, that's that width right there, times 4, because that was a given length of the trough. So we need to figure out what W is in terms of Y. Does everybody agree the rectangle is going to have area 4W? Right, the length of it is 4, and the width across the face of that semicircle I'm going to call W for a moment. But we can't integrate with a W in there. We have to turn it into Y's, which is what these functions are for.
So the thing is 4 meters long?
Yep. Yeah, so that's given to us up there, 4 meters long.
Okay.
Okay, so now we've got to figure out W. W is the distance across the face here. There are 2 ways to think about it. One is the really basic way that we take, it's a horizontal distance, so we take the right x and subtract off the left x. The right x is this, the left x is that. So we have root minus root. So we get double the root. We get 2, so I'll write it out in gory detail. Minus root. So this turns into double root. So that is using our basic concept that a horizontal distance is right minus left. You can also conceptualize it slightly differently. You could think to yourself, if we look at this right edge there, this function is measuring that purple distance, and by symmetry, we just double that to get the width all the way across. So you could think of it that way also, that this x is measuring half of W, so we just double that. and we'll get all of W. So either way is totally fine as long as one of them works. So now we have a 9800 out in front once again. That 4 is constant, so it can come out to the front also. So here's what we're left with in terms of variable. 1 minus y, the distance, and then the W, we'll pull that 2 out in 1 second. But we can pull that out. So we have that. So this 4 right there is that one out in front, and then those two guys turn into that. And then the W, that is this stuff right here. Everybody okay with that? Now, you don't have a lot of techniques of integration. The main one you have is substitution. If you are going to substitute, you look inside the square root. What is the derivative of that?
Negative 2y plus 2.
Negative 2y plus 2. Do we have a negative 2y plus 2 out in front? We can certainly make one. If we don't get frisky and take the 2 all the way to the front, if we just distribute it into here, we have 2 minus 2y, which is the same thing as minus 2y plus 2. Commutative law of addition, if we wanted to just reverse it so that it matches kind of, if we think of this derivative as negative 2y plus 2, if this 2 goes in here, we get 2 minus 2y, which we could just rearrange if we want. Now we're gold. Now we are set for integration. So we let u equal negative y squared plus 2y. So du is negative 2y plus 2 dy. Which is right there. So our limits of integration, we'll deal with this multiplication by 4 in a minute. So we have the integral. We no longer have y limits of integration because we're switching to u. So we're going to have the square root of u. And then all of that is du. And if we switch to u limits, we'll plug those y limits in up here and get the u limits. Or we could put placeholder limits and switch back to y and use the y limits with a conversion back if we want. Doesn't matter. These are pretty easy to convert. If we plug in y equals 0, we get u is equal to 0. If we plug in y equals 1, we get 1. They're actually the same. So in this case, it's not going to matter at all. So we have 9800 times 4 times u to the 1/2 add 1. That's 3 halves. Divide by 3 halves. Multiply by 2/3. 0 to 1. So we're going to have, I'm going to multiply the 4 and the 2/3. So we have 8/3. We'll deal with all this multiplication in a second. Plug in 1. Plug in 0. We just get 1. So all we have to do is multiply 9800 times 8/3. And we will have it. 9800 times 8/3. Let's shrink you way up. 9800 multiplied by 8/3. And then we want you as a fraction, not a decimal. Unless it asks you for an approximation, you do not round. And those decimals are all rounded. So once again, we're dealing with an application that has units. So we need to put units on our answer. So we're going to end up with 78,400 over 3 joules, or newton meters, either one. Questions?
Let's see, Bill, well, since I went over U substitution back in Calc 1, the way you get the limits of integration with the U substitution, you went over that like really quick, like, oh,
Yeah.
it ends up being the same in this case.
Yep.
What's the,
So we're plugging this 1 in here for the y. We're plugging this 0 in here for the y. So this is, this is how you exchange y's and get u's. If you plug in a 0 for y, you're going to get your corresponding u. If you plug in a 1 for y, you're going to get your corresponding u. So that equation that you use as your substitution is how you exchange y's for u's. So you plug in the corresponding y, you'll get the associated u. So anytime you see a semicircle, you have to gulp because you've got, if you haven't yet, go to that review page that I have up there and make sure you get your semicircles down because they're all over the place. And think about this carefully on how you can get to this W by doubling this or doing this minus that. Okay, let's try a shape that's a little less overwhelming. A cone. Oh, wait, we didn't finish that one. There's a couple other secondary questions. If the length of the trough is doubled, is the required work to empty it doubled? What do you think?
Oh, maybe. Just because I'm saying, like, the 4 made it all the way to the end, and so then if the 4 became an 8,
So yes, right? That doubling the length didn't change. The height is the thing that's variable. That's the thing where you get the minus y, the whatever it is, 1 minus y here, right? But the length is just this constant of 4. So if it's doubled to 8, the 8 double comes out in front, and you've just doubled the 4. So yes. So this will be a yes. Find the work required to pump the water out a vertical pipe that's 2 meters long. So part C, what is the only change for part C? So if we look at this, we're zooming in on distance, right? This is distance. That's the only thing that's going to change. If we pump it out that pipe, and that pipe is 2 meters long, what does this distance become? 3 minus y. Because the trough is a meter high, and then there's a 2 meter pipe, so each slice is going to travel 3 minus y instead of just 1 minus y. So it's the same as above with distance equal 3 minus y instead of 1 minus y. So it'll all look the same except for that one thing.
Because that 1 minus y was used for U substitution, how would that work? If
You would have a slightly different substitution, but it'll be comparable though.
Okay.
Yeah, if you go through it, you'll just have a slightly different situation in here, but it will still work out. Okay, let's take a look at another shape, a cone. So the height of our cone is 6, and the radius is 1.5. Same thing, we want to empty it out the top. All right. So let's take a look at a representative cross-section. And I should rewrite this slide. Now I'm going to have 2 R's. So this one is given to be 1.5. So let's cross that R out and just write that as 1.5. And then the variable r is going to be for your representative cross-section. That radius is going to get bigger depending on where you draw your slice, your cross-section. Okay, and the whole height is 6. So let's first just start with our generic formula. We know that work is the integral of ADD volume. This tank, this vessel, is 6 meters tall, so we're going to integrate from 0 to 6 to get it all out. Acceleration, we know right away, we know the acceleration is 9.8, and the density, because we're dealing with water, is 1,000. Our representative cross-section is at a random height of y. So that y is measuring from the ground up to there. The full distance is 6. So what is the distance traveled by our cross-section? We're going to agree, 6 minus y. If the full distance is 6, and this distance is y, that complementary distance is going to be 6 minus y. It's the upper minus the lower. So upper y is 6, lower y is y, 6 minus y. So that is going to be our second D, 6 minus y. Now the hard part, the volume. Not the volume of the tank, it's the volume of a representative slice. So now we add thickness to this cross-section. That thickness is going to be a dy. Now we have a slice. The volume of that slice is the cross-sectional area multiplied by dy. So now we need, in here, area, cross-sectional area times dy. This will be volume. All right. So let's come off to the side here. And we know that the cross-sections are circles. We have so we're finding the area of a disk, which is pi r squared. We need to know the radius. The radius is variable. It depends on where you draw it. And that radius is horizontal, so it's an x value. So we need to know the equation of this line, because that's measuring the distance off of the vertical. We need to know the equation of that line with which letter isolated. X, because we're measuring horizontal. So we find the equation of that line, and if we isolate the x, then that's going to be measuring horizontally from the y-axis. That line's really easy to find. It goes through the origin. Y equals mx plus b. The origin is 0, so y equals mx. So y equals slope times x. The slope is up 6 over 1.5. So this line is going to be y equals 6 over 1.5 times x. 1.5 into 6 is 4. So it's y equals 4x. All right. But now we need to isolate the x, because we're measuring horizontal for that radius. So we're going to isolate the x. X is going to be y divided by 4. That's the radius. The radius measures from the y-axis over to that curve. So our disk area is going to be pi times y over 4 quantity squared. So that's going to be pi over 16 multiplied by y squared. That is the area that's going to drop in here. So let's pull out the 9800 first. 0 to 6, 6 minus y. Area is going to be pi divided by 16 multiplied by y squared dy. So that is that. Pi over 16 is yet another constant, so we're going to drop that out to the front. 9800 pi over 16. We're going to distribute the y squared and get 6y squared minus y cubed dy. We'll just hold off on these constants out in front. We can simplify them later since it's not obvious. So this is going to be 2y cubed minus y to the 4th over 4 from 0 to 6. Zero gives us nada. So all we have to worry about is the 6. Plug in 6, we're going to get 6 times 6 times 6, which is 216 times 2. So 432. Somebody double check me on that.
That's correct.
Thank you. And then here we're going to have 6 4 times, but 2 2s are going to cancel, so it's really going to be 6 twice and then 9. 6 twice and 3 twice, so 9 times 36, whatever that is. 9 times 36, which we can type that all in and figure it out. So think about that while I type it in, and make sure you understand where all those bits and bobs came from.
And that's 36 times 9 right there, not 369.
Correct.
Okay.
Corbin, question?
6 to the 4th over 4 isn't 369, that's 324.
Yeah, it's not 360. It's 36 times 9.
Oh, okay.
Because I did 2 6s, it's 36.
I didn't see that.
You see it?
dot.
Yeah. Yeah, that dot I should draw bigger. $36 times 9 there, yeah. So let's make that a bigger dot. All right, so when all is said and done, we get 66,150 multiplied by pi joules of work. All right, questions on steps there? So we're still using those basic concepts we used from the very beginning. Horizontal distance, x minus x. Vertical distance, y minus y. Those two really basic ideas are used repeatedly in all these applications. All right, let's go back to the chains and the ropes. All right, did I go one slide too far? So, coiling a rope. Notice the density that they give us here. Is that 1D density, 2D density, or 3D density? One-dimensional density. That means we're going to have one-dimensional mass. That means that the diameter does not matter, because we're imagining the rope as you know, one dimension. So that diameter, we don't care about that, because we're working with 1D density. So now let's look at our formula for work. Our generic formula is ADD volume. And when we think of this volume, we are thinking of cross-sectional area multiplied by dy. If there's no cross-sectional area because we're 1D, what does that become? Just dy. Right? This is area multiplied by dy. 3D density down to 1D density, you took away 2 dimensions of length. Taking away 2 dimensions of length, right there, that's gone. So our formula for a chain or rope is just ADD multiplied by dy. Okay. So it's one-dimensional, so it feels like it should be easier, but it's sometimes when you're getting rid of things, it doesn't play out as easy as it seems like it should. So let's go through this then. So we're told we got a 60-meter rope, and we know the density, how much work is needed to pull the entire rope up to the ledge that we're sitting on. So acceleration, 9.8. Density, 55. Distance traveled. Let's draw a picture of our rope. That's 60 meters. A representative cross-section is just a link or a segment or a little tiny chunk of rope. That's y. So that's measuring from here to here. So what's our complementary distance? How far does that segment of rope have to travel to get to the ledge?
60 minus y.
60 minus y, complementary distance. 60 minus y. 0 to 60, we want to lift up the entire rope, and we're done, dy. Cross-sectional area is gone because we're in one dimension, so we're dealing with one-dimensional density. So the 9.8 and the 55, those just pop to the front. And we're integrating 60 minus y, which is 60y minus y squared over 2 from 0 to 60. The 0 doesn't give us anything. So we have 9.8 multiplied by double nickels. And then here we're going to get 36 with 2 zeros, so 3,600 minus 3,600 divided by 2. So minus 1,800. So all we have to do is multiply that stuff together. So we're going to have 9.8 times 55 times 1,800. And that's our work done. So our work is going to be 970,200 joules of work. Question on the rope? Yeah.
A little bit more of a general question.
Sure.
But so the acceleration, that seems to not be impacted by however fast the object is moving in the direction you're trying to.
Right. Yeah, work done. Doesn't matter how fast you pull it up.
Okay.
Doesn't matter the speed.
You're like fighting against.
Right.
Okay.
Yeah, so the work,
Doesn't matter how fast it's done, it's the amount of work that we're measuring.
Yeah, the work will be the same whether you pull it up fast or pull it up slow. It may not feel like as much work if you pull it up slow because it's spaced out over time. All right, let's try another one of these one-dimensional things. So let's go to the chain, which of course is the same as the rope. Okay, so we've got a 30-meter chain hanging vertically from a cylinder that's attached to a winch. There's the cylinder. Here's the rope or chain coming down. 30 meters. Assume there's no friction in the chain, has density 5 kg per meter. How much work is required to wind the entire chain onto the cylinder using the winch? So first thing we notice is that we're in 1D land because the density is per meter. So as soon as we're in 1D land, we know that our work is not going to be ADD volume, it's just going to be ADD times dy. Normally we have the volume in there, the volume of a slice, which is area times dy, but the area gets nixed because we're taking away 2 dimensions from the density. So we take away the area. So to find our work, acceleration is 9.8. The density is given to be 5 kgs per meter. When we look at a cross-section of chain, we have a single link of chain at a random height of y. How far does that link have to travel? 30 minus y, complementary distance. So 30 minus y. And because we're dealing with 1D, we have no cross-sectional area to put inside there. It's just going to be a dy. And then we want to jack, we want to hoist, we want to winch the entire chain up. So all the links from 0 to 30. So the 9.8 times 5 pops to the front. It is constant. Now we integrate this variable piece, and that integral will be 30y minus y squared over 2. That'll go from 0 to 30. So 9.8 times 5, let's see, what do we get there? So 30 times 30 is 9 with 2 zeros. So what's that, 900? 900 minus 450, so that's going to be 450.
Did it say that 5 somewhere above the density? Cool.
Yeah, so that density's got to be given. Everyone see why it's 450? What's that? So that'll be our work, 22,050 joules.
Now, I noticed it was kilograms per meter. Would that change the number that we would have to start with?
Because this is kilograms?
Yeah, 1,000 grams, or I'm assuming
Joules is with kilograms.
joules is with kilograms. Okay.
Yeah, that's the, did we have one with grams that we didn't convert?
I don't think so.
Yeah, so kilograms should be
So pay
the, kilograms is the standard
So
for a joule.
pay attention to that unit. If it changes, it'll change.
Yeah,
to
that,
joule.
if that was grams, then we'd have to be a little more careful.
Yeah. Divide by 1,000.
Yeah.
Divide that by
By-
5,000
yeah.
if it's the case.
So, up the ante a smidge. Let's suppose we have a 50 kg block at the bottom. If we're going to lift a block vertically, all we have to do is mgh. So when you're winding things, the mass of the rope that's dangling is changing, right? Each moment there's less mass. So that's why we have to have that integral in there, because it's changing. But if we just lift a block, that's the simplest scenario where we can just multiply the 3 to get force times distance. Force is mg with gravity. Force is mg for gravity. And then we multiply by distance. So if we're lifting a block, it's just going to be mgh. So this part, B, work for just the block will be mgh or mg distance. And the mass is 50 kgs, gravity is 9.8, and the distance it travels is 30. So that 50 kg block is just going to be pulled up 30 meters. So this will be the work just for the block. And then the total work would be the sum of the two. So for the block, we just need to do mgh, whatever we get here. So 9.8 times 50 times 30. So 14,700. Joules. And so then we're just going to add that plus that together. So total will be 36,750.
Yes.
So again, in this case, work is force times distance. So force times distance. So that's the simplest scenario for finding work, force times distance. All right. And each of those is constant in this case. So let's take a look at this thing. This shows you a big difference between the way a math teacher will do this problem and the way a physics teacher will do this problem. Here's the scenario. We've got a chain that's 40 meters long, 1 kg per meter density. How much work is required to wind it halfway up? Here's how a math teacher will do it. The reality method. Math teacher is going to look at this and say, oh, okay, so we're going to wind up the orange links, right? The black links are just dangling. So the black links are acting like a block. So here's the initial state. We wind it up. The orange links are up on the winch. That's what's left hanging. It's the same thing as if you just imagined all these black links as one block. Right? They're just being lifted. So this is how we would imagine it as a math teacher. So the stuff that's moving onto the winch is from a height of 20 to a height of 40. And then we're going to add the MGH for the block, the bottom black links. All right? Make sense? That's how I would think of it. Well, I remember the first time I taught this 20 years ago or whatever it was, I looked in the book. Actually, it was 30 years ago. That's sad. When I looked in the book, in the answer key, they integrated from 0 to 20. I'm like, what? 0 to 20? Here's the way a physics person is going to think of it. They're going to think of it, here's the initial state, and in the end, we want to have 20 meters of links hanging. Well, let's just imagine the lower links mysteriously jump to the top, and let's imagine the top ones is not moving. We still end up with half the chain dangling from the winch. So if you do it this way, there's no block. These things are just left dangling. They don't move at all. And through some abracadabra business, you can say, oh, it's just these 20 that are going to move. And so we just do our, so here's the reality method, ADD length plus the MGH. And here's the other method. Here, the distance, notice the distance that they're traveling, though, is 40 minus y, right? Versus the distance, well, it's going to be the same. Still going to be 40 minus y. But they're traveling 40 minus y, but they're going further because it's 0 to 20. So the numbers are going to be bigger over here. You're subtracting off the lower links. You get the same answer. So those are two different ways that you can sort of, if you're only partially winching the chain up, you can think of it in two different ways here. So look at those details and, sort of think about it, what the difference is. Okay, so the last thing in this section is force and pressure. And we're only going to do one type of example from this section. We are going to imagine the force on a wall or a window. So let's see. So just force on a wall or window. I've got two videos up under that weekly video thing that are very good to watch to understand hydrostatic pressure. Super important to watch. Let me ask you a question. So let's suppose that we have a dam. So this wall is holding back water, okay? So there's all this water behind this dam. So let's just imagine we've got our dam, and we've got a mile of water. What do you think will happen to the force on the dam if we extend this mile of water to 2 miles? What was that?
It'd be less.
There'd be less force.
Or pumping and pressure.
So what do you think in terms of the force on it?
Gonna go up.
Maybe more because it's less surface area that it's touching.
You got more water behind the same wall. It's gonna go.
Why do you think they build those dams so damn big? Because the force is the same. If you have 5 inches of water pressing on it, or 5 miles of water pressing on it, same force.
Okay.
Because when you understand hydrostatic pressure, water is pressing in all directions simultaneously. So if you kind of zoom in and you imagine 2 particles of water, they're sort of counteracting each other when they're next to each other. So you can have 1 inch of water or 100 miles of water. All the stuff that's past the 1 inch is canceling each other out, and it really just matters the film of water that's right on the wall. So it doesn't matter how far back the dam goes. And so those 2 videos give you a good sense of hydrostatic pressure. So when it comes to finding the force on the dam wall, it becomes very similar to what we just did finding the work in a lifting or pumping problem. It's just that we do ADD area instead of ADD volume because we've taken away one dimension. We're not looking at the volume anymore, and it doesn't matter how much water is behind it, so we're just looking at the face of the dam. And we're going to use the exact same acronym, except that instead of an incremental volume, we're going to look at an incremental area. The area is not the area of the face, it's the area of this strip. So when you think about pressure, pressure increases as you go deeper into the water, but if you take a very thin strip along the dam, you're going to have constant pressure on that thin strip. And so the idea is another Riemann sum type of thing, that we're going to find the force on this little strip based on how deep it is, the force on this strip based on how deep it is, add them all together, take an integral, and we are going to have an integral that is going to be identical to the integral we just did, except we will have area instead of volume at the end. And that's what this is all representing. We're still going to have ADD. This is going to be area then. The width of the strip times the height of the strip, the thickness of the strip. Thickness would be the dy. And you can look carefully at these units just to convince yourself. When we look at pressure, pressure is force per unit meter, per square meter, and we call that a Pascal. If you want to use Pascals, you can. Newton per meter squared. So pressure is force per square meter, which we call a Pascal. So just going, we'll finish these up on Thursday, but the idea will be the same. We're going to do integral ADD area, and by area we just mean the area of that red line. So the width times dy. All right, we'll stop. See you on Thursday, unless you want to stay and do more math. Feel free to stay and do more math. I'll sit around here until 11:30 doing.
Man.
If 2 hours and 15 minutes isn't enough, we can do more. Do you have a question on OneNote? Have you opened it yet?
So what was your name again? Vio. Vio, I know we're in the same group in the physics class. You meet me to Excel?